Welcome to Happy Path Programming. I'm Bruce Eckel.
I'm James Ward. All right, well, Happy New Year. Welcome to Happy Path Programming. So you want to tell us about Winter Tech Forum, the current state?
So the current state of it is it's the last week in February, so that's coming up fast. And you go to wintertechforum.com to find out about it. We have officially 30 spots, and that's because on Friday we have the cross-country ski or snowshoe out to the yurt, and there's a yurt dinner, and we have 30 spots for that. And you want to sign up soon because I have to release any unused spots 2 weeks ahead of the conference.
So it's just one of the fun activities we have at the conference is going out to a yurt in the woods at night and maybe looking at stars if it's clear. And,
and have a really nice
dinner.
Yeah, very nice dinner, and that's all part of the conference fee. That's taken care of. But this year we only have 30 spots for that. So, I mean, if you really get desperate at the last minute and still want to come and we don't have any spots left, well, you and whoever else in that
in that situation, wonderful restaurants.
Yes, we have you can all go out in group, but we have all kinds of. It's a lot of activities, and it looks like it's just all fun, and it is, but we end up talking about tech almost continuously throughout the whole thing, except when we get together in the rental houses and play games. Then,
it's true.
Well,
some good board games.
Yeah, that usually distracts us from the tech for a while. But you'd be surprised at it's like and also the tech conversations tend to be more relaxed because we're doing the unofficial things, and so people feel more comfortable talking about this or that. So
about their horrible manager
or whatever it is. Because and we will be recording some of the sessions at least, and putting them up as podcasts.
Give that a try.
Again.
Okay, so let's get going. So today we have with us Adam Warski, who Adam, you have done so many amazing things. I think mostly what I've seen is in the world of Scala with libraries and all sorts of great stuff. So we're going to dive into some of that today. So welcome, Adam. Great to have you.
Great to be here. Thanks a lot for the invitation.
Yeah,
right. And we're talking to Adam from Warsaw, Poland.
Yeah.
I mean, he's from Warsaw, Poland. So
exactly.
I would like to
unless you are close by, it doesn't seem so.
Right. Yeah. It's a very good internet connection. I would like to start by giving you my hypothesis of how Loom works and have you correct me, because it seems like you know an awful lot about that, and there's still a lot of mystery to it. So here's the way I think it works. It's a coroutine based system. So it's got coroutines, and the problem normally with coroutines is that a compiler has to know where the suspension points are so that it can build continuations at that point, and you can have a safe suspension and resumption, and also cancellation and error reporting and all that kind of stuff. So the trick that I think Loom is doing is because the Java virtual machine has, as it's executing these JVM instructions, it knows where safe suspension points are between, maybe special JVM instructions, maybe every JVM instruction. I don't know about that. And so it can insert those without you having to explicitly put anything in the code and create. I'm sort of guessing it's creating the continuations dynamically, but I could be wrong about that. So am I anywhere near?
No, I guess it's quite close to how this works. So as far as the suspension points go, as far as I know, things work very similarly as with normal threads, right? So the whole idea behind Project Loom is that the virtual threads, which are introduced as the first component of the project, as a stable feature of Java. So these virtual threads should work exactly the same as normal threads, right? So we had threads in Java for, I guess, forever. You probably know this way better than me.
One or something.
But broken threads, I think it's safe to say.
Yeah. Well,
and
yeah, these are like in the Loom terminology, these would be the platform threads or the career threads, right? So they are still there, but next to them we have the virtual threads. And from an API point of view, they work exactly the same, meaning that the suspension points, or the points where there's a context switch, right, between executing one thread and another, they are the same in both cases. And these are the blocking operations, right? So whenever you wait on a semaphore, you acquire a lock, you issue an IO operation, you read from a socket, and so on, right? So these are the suspension points. So there are like no special JVM instructions that are inserted. And it's not.
Did you say there are special?
No, there are not.
There are none. Okay.
As far as I'm aware, I don't think so. No.
Yeah,
it's just
but the JVM knows the blocking.
Yes,
it knows what a blocking call is, essentially.
Right. Well, there's a couple. Like, if you go down there's like wrappers, of course, like in terms of IO and new IO and so on. But I guess it's just a couple of constructs. Like every like synchronization primitive, like every lock and every semaphore and so on, boils down to calling lock support.park, which is a special method which actually parks the thread, right? So that's the suspension point. And so what's different in Loom is like the suspension points are the same. So they are quite coarse-grained, right? It's not like the JVM runtime can just
suspend at any
switch
point.
context. Yeah, switch context at any point. It's only when there's a blocking operation.
Ah, okay. But it can. So, my understanding of the normal threads or whatever previous threads is that they were just suspending based on the operating system. It was saying, "Oh, you've had enough time this task. We're going to suspend you wherever." And you're saying that, "Oh, well, here the suspension points are actually detected when you make an identifiable blocking call." And the JVM actually knows where that is, and it says, "Okay, we can suspend it at this point." So it's much more precise.
Yes, well, I think it knows about more or less the same as it knew before. It's just doing different things, right? So before it was doing a full context switch, meaning that it was like an operating system level context switch, which is quite expensive. It's slow to do at scale. The stack size that needs to be switched
something with the
quite,
stack, yeah,
right, and
quite
so that
big.
Limited, yeah,
right. So with Loom, that is all optimized. So the time to switch between two virtual threads is much smaller. The stack that needs to be put aside is much smaller as well. It's optimized in various ways. So
right, because it's just storing. I'm saying it's creating a continuation, which is just storing the things that it knows need to be stored because it can know those things. Whereas with an operating system context switch, it just goes, I don't know what you're doing. I have to save and restore everything. So that's why.
It's actually doing some quite clever tricks. So there's a talk from JVM Language Summit from last year, which talks about it in detail. One of the developers talks about it. So he's, I guess, the best person to talk about such things.
The internals of how it's all implemented.
Yeah, but one of the tricks that I remember is that the first time you suspend a virtual thread, so you want to context switch, the full stack is put aside and another virtual thread is run in its place. But the second time you do it, it's only the difference in the stack between these two blocking calls that is actually needs to be put aside, right? So that over time, if you block a virtual thread often enough, the amount of stack that you actually need to update in your memory in your side memory is very small. So this makes it much faster.
It is doing it dynamically then.
In what sense dynamically?
Some dynamic analysis of the diff of the stack.
Right. So it says, okay, the first time we save everything, the second time we look at the diff and we go, oh, well, we only need to save the things that
yes.
were changed.
Yes.
Okay, but it's doing that at runtime.
Yes, of course.
Okay,
yes.
Okay. Yeah, whereas
you can't really know what's going to end up being blocking, right? It's an undecidable problem.
Sure. Yes. Whereas with compiler level things, the compiler knows, oh, you've within this scope, you've only got these variables that I need to save, and so it does that analysis at compile time, whereas Loom is doing it at runtime.
Right. I think
like in Kotlin coroutines, how the compiler is kind of unraveling all that into the state machine at compile time.
Right.
Or something.
Yeah, it can build that. Because
in Kotlin, the compiler has to do a lot of things, right? It needs to transform the whole program into continuation passing style, into a state machine. So that's a whole big transformation. And that's why you need to annotate each function as suspendable, right? So that it can properly do the transformation. I don't think there's really anything that the Java compiler does regarding to virtual threads, right? It's all in the JVM. So in that sense, it's all dynamic. Yes.
So because it's in the JVM, that means Kotlin can use it and Scala can use it, right?
Yes, sure. And any JVM language can use it, of course.
Okay, and your aux library for Scala uses it.
Yes.
Maybe give us the rundown on aux.
Yes.
Yeah. So how aux came to be? So it's still mostly a research project, coming from the fact that for a long time we've been using functional effect systems in Scala, and I guess you've worked with them, you've played with them quite a lot as well, right?
Well, Zio.
Yeah, mostly in the world of
Zio, Cats Effect, Scala Z, Futures to a certain degree fall into this as well, right? And they have some very interesting properties. Like they make certain things very nice. The code is very elegant. It's very expressible. You can very elegantly define concurrently running operations. You can, they have fibers and so on and so on. And that's all great, right? And there's referential transparency. You can do refactoring. There's a lot of nice features. There's a couple of bad features as well, right? The syntax is completely different, which people have to learn, and people complain about that. The stack traces are mostly useless. And so there are some problems with the approach, right? But still, there's a lot of benefits. Like in the pre-Loom world, I guess the benefits really outweighed the costs, especially when you had to use concurrency. So now Loom comes along, right? It took some time, but it's finally here. So now we end up having an asynchronous runtime inside the JVM. So something that these libraries before implemented at the library level now is part of the JVM, right? It's more or less the same approach that they had, right? We have a pool of platform threads on top of which we run many, like thousands or tens of thousands. It was fibers in Zio or in Cats Effect, and in Java it's virtual threads. So now the question is, at least my question is, once you have this asynchronous runtime in Java, is there still any merit into using the functional approach, the wrapped approach, right? Or the monadic one? That would be most precise. So are there like some features of this monadic approach which justify paying the cost of the syntax overhead, of the stack traces, of the virality, and so on?
And instead, can you just punt to the JVM's capabilities around async and virtual threads and just say, hey, you don't need to build your own fiber scheduler on top of the JVM. Just use the JVM's lightweight
Exactly.
threads.
The asynchronous features, I think, were the driving force behind actually implementing Cats Effect, Zio, Futures, and so on, right? And as time progressed, people really polished these solutions, and they came to have a lot of other features that are very nice, like referential transparency, right? First we had callbacks, then we had futures, and then we had IO. So that's like a evolution of how this approaches worked. But still, the core problem was asynchronous, right? We wanted to have scalable programs which can handle, tens of thousands of concurrent connections, not being limited by the amount of threads that you have.
So just as a quick side note to this, I think in most kind of traditional blocking-based I/O servers, let's say, you typically wouldn't want more than, let's say, 1,000 threads, and that means that you if you've got an HTTP connection coming in, and then you've got a database connection, you're pretty limited on your kind of max number of concurrent connections that you can have through a given system.
You hit scaling walls, and you have to change your architecture to adapt to those.
And there was some trade-offs that kind of put that arbitrary limit on what you can do. One of them was the context switching of these platform threads. Another one was the memory consumption of each thread, because each thread needs a stack size, and that gets allocated to every thread individually. So those limitations were in some ways kind of arbitrary to the way that blocking IO worked on the JVM, kind of pre-async connection, Netty, whether it's Netty, NIO, or other ways to do async IO. And then the complexity of programming for async IO led to the history that you were talking about with futures, and then IO monads and fiber schedulers and all that kind of stuff that we've seen.
Exactly. So I guess when I started my career in Java, that was like, 15, 20 years ago, we were using the thread per request model. So something that we are now again revisiting, right? So each thread, each request got its own thread, and it was doing everything on it, right? And the way to scale applications, as you say, was to increase the number of threads. Like there was like the Tomcat connector or something where you can put in the number of threads, right?
Yeah.
And this worked up to like 100, 200, maybe 1K threads, but that was like stretching the limits of the operating system, right?
Well, and oftentimes I think a lot of these systems were just sitting in wait states. These connections were just waiting for something to happen. Mm-hmm. And so you were kind of arbitrarily gating
holding all that memory and everything.
Yeah. And so you were not really fully utilizing your systems in the way that
well, plus you could write a program that would work fine on one machine, but then put it on another machine that didn't have as much memory, and it wouldn't work.
Yeah. Mm-hmm. And for optimization, like the optimal solution is that you actually have near the same number of threads as your OS threads, and that's primarily due to context switching overhead. Is that the right way to think
I guess as you said, both context switching overhead and memory consumption. I guess back then we didn't have as much memory as now, but the stack sizes were not much smaller, I guess.
Yeah.
So that was a waste.
Like some GC thrashing and memory allocation overhead, and some of those things come into play as well.
Yeah. So it was a waste on one hand, because it was a waste of resources, because everybody was just waiting for the DB to come back with or something like that. And on the other hand, you hit your scaling limit very soon, right?
Yeah.
So people came up with the idea that we can actually do better, and we can schedule some operations and asynchronous, and just wait for multiple results on one thread, and that's how async came to be, right? So and as we said, we had like the callbacks first, then the callback hell was bad. So people came up with futures in many languages, like not only Java and Scala, right?
Yeah,
I guess JavaScript.
Lots of different future implementations out there.
Yeah.
Well, also that the constraints that we had, I would say, because you couldn't just do a thread per request model, that it made your programming more complicated and more difficult to maintain.
Exactly. Yes.
Okay.
Yes, but
and
it
that was maybe
allowed
the impetus for
scaling,
IO.
right?
Yes,
Yes.
and then
IO
scaling
monods.
again. Yeah.
Yeah.
So that's exactly the premise of the problem that Loom tries to solve, right? They want to make this simple again. So they want to get rid. I guess there's like three main motivational factors that they want to get rid of. And the Java, well, of course they focus on the Java ecosystem. But even in Java, if you work with futures or with reactive extensions, the syntax is just, well, maybe especially in Java, the syntax is just ugly if you have to do flat maps or things like that.
Yeah.
So I have another question. What do you get any parallelism benefits? Like if you have, you have multiple tasks running, and you're just like, is it going to take all of your cores and distribute them across these tasks and stuff like that? Is there any of that there, or is this strictly IO bound issues?
So if you want to improve performance of your code, with Loom, it will be mostly visible in blocking operations. So if you have CPU intensive code, no, that won't improve. Like you can, of course, create as many virtual threads as there are cores, but it's usually 8, 16, 24. You can as well create platform threads for that, so it's not such a big difference, right? So virtual threads matter once you have 1,000 of them or 10,000, right? So this focuses on I guess a more web app type scenario, or like a business application, however you call it,
or just
where
IO in general.
IO in general, yes.
Yeah,
yes,
right.
yes. Where you have some incoming connections, you do some database work, you go to Kafka, you go to a web service, WebSockets, and so on.
Yeah, WebSockets are definitely an interesting example where a lot of times WebSockets are just idle, and you don't want to have thread per connection, thread per platform, platform thread per connection, because then your WebSocket server doesn't scale.
Yes. By the way, for WebSockets, I guess actors are a very elegant solution, but that's like a completely different topic. But the actors are also quite, I guess, a similar answer. Maybe a bit evolved answer comparing to the future approach to exactly the same problem, right? You want to scale.
Well, right, because an actor to the rest, when you're inside of an actor, the rest of the world looks like IO, even though you're staying within the, you're inside the program, you're not going outside of the chip, but the other actor you send a message to, and then you're waiting on a result or whatever. So is that a reasonable
way this as well, but also the fact that you are multiplexing many actors to run on a single platform thread, right? You are just exchanging which actor runs at a given time. So that's very similar to how fibers work. That's similar to how virtual threads work, or coroutines in Kotlin. It's the same thing.
It's like the mapping of many virtual things to a few physical things.
Right. So first of all, is actors any part of Ox, or have you been seeing, are there actor
going back to Ox, because we started from that. So the research question, let's say my research question is, once you take away once you have the asynchronous runtime inside the JVM, is it still worthwhile using the functional effects approach, right? So I tried recreating some of the high-level concurrence operators that you get with the functional effects systems in a direct style. So direct style, I guess, is the name for the blocking style approach, right? Where you just
write your code as if directly. It's synchronous.
Yes.
But it's actually not. in terms of its execution,
it depends at what level you look at it, right?
Yeah,
it is blocking if you look like from a source code level, but of course, if you look at what's actually happening underneath at the VM level, it stops to be blocking. But that's hidden from you. Like your code looks as if it's just doing a series of blocking calls, and you don't really have to worry about where these operations are going to get scheduled, right? So that's all handled by the JVM.
So instead of having to use a monad with a flat map to sequence things together, you instead just sequence in direct style in your code, but you underneath the covers, because of the JVM's async capabilities with Loom, it all gets kind of unraveled into the more efficient way to execute those operations.
Right. Yes, exactly. So one component of Aux are these high-level concurrency operators, like racing to computations or running to computations in parallel or doing some collection operations in parallel. And that all turns out very nice partly because of Scala's flexible syntax, partly because of what Loom gives you. So that's one part. And another part is that, well, when we go back actually to the blocking style concurrency, it's like if you take a look at the experiences of people doing concurrency in a blocking way in the old style threads, it's not that safe, right? It's very easy to get into a deadlock. It's very easy to get into a race condition. And it's going to be the same if you are using virtual threads as well, right? So these problems don't go away. So if you just try to program using locks and semaphores and threads which can run arbitrarily, you will get into the same problems, right? So we probably don't want to go back into that world. So we probably want to look for something better. And that's the second component of Aux, which is also explored by Java, but in a slightly different syntax, and that's structured concurrency. So structured concurrency is something that I think originated in Python, at least was popularized by Python. So I think the term actually was first used by a guy who worked on 0MQ, if you know the project. So I guess it's more like C. But then there was a Python library, and there's a very popular blog post, Go considered harmful.
Go statement considered harmful, yes. Yeah. And he created a library, and I was initially saying, oh, well, that's the one to use. But then it turns out that all of those features have been incorporated into the Python standard libraries concurrency.
Which I guess simply shows that it was the right answer to these problems, right?
Yeah.
So the pitch on this is that by using these higher level abstractions lumped into the concept of structured concurrency, we can more easily avoid deadlocks and race conditions and that sort of thing when we're writing concurrent code.
Yes, exactly. So I think the idea is still to avoid using locks, to avoid using semaphores and so on, if you can. Well, maybe semaphores are good for like rate limiting, but locks are especially bad when it comes to programming. So I guess you would still want to avoid it. So we need to build some other tools to still do concurrency. Like there's certain things that you can do on the high level, like probably like maybe 95 of your needs will be satisfied with race and power. So racing to computations or running them in parallel, but the 5% still needs to be catered for, right? So that's when you can actually create scopes where you can run threads on your own. So that's one thing. And then you want to communicate between these threads. So for communicating between these threads, Aux proposes channels. So that's
communicating
like the
sequential process model.
Yes, kind of. So that's also inspired by Go. I think Go might not be a language which brought a lot of innovation in terms of features, let's say.
No.
But I think it did show that the channels model is actually quite useful and people like it, and it's used successfully in many applications. So maybe we can learn from that and actually try using it in both in Scala and in Java.
So quick side note on this, thank you. You contributed the Aux version of the Easy Racer client, which is a little.
That's a very interesting project.
Yeah, so a little playground for structured concurrency, and the Aux one is the most concise and expressive out of all of them. And I'll someday have a blog post that goes into all the details of that. But it really makes Aux's programming model for structured concurrency, those high level things, really shine. But one little interesting side note. is when I was building the Rust version with Bruce and who else was helping. That was at the Rust Summit or something like that. This is going to loop back around to channels, because I think what you're highlighting is that there's times where the race and collect all par, or whatever it's called, like the ability to do multiple operations in parallel through structured concurrency. There are cases where that model, the 5%, where that model doesn't fit a particular need. And when we were building the Rust version of this, we discovered that the Rust race is a macro. This is the structured concurrency race, is a macro, and it only takes two. You can only race two things. And as you know from Easy Racer, there's
I remember
a few
from
use
from your
cases
podcast,
where you have to do race more than two things. And so we had to find a different route to do the race, and we ended up using the channels in Rust to implement that our own race, essentially, that could support more than one. And so am I understanding this correctly, that channels in some ways, the existence for it in Ox is to give you the escape hatch when the higher level structured concurrency APIs don't fit what you need?
Yes and no. So I guess for example, for implementing race, you would just create a scope. So a scope is a syntactical construct which delimits the lifetime of threads. So that's like the central idea behind structured concurrency, right? So that the structure of the code determines how long your threads live. So this makes it easier to understand your code.
And that's the analog of what in the Go statement considered harmful. That's the analog
nursery.
Of
he called it nursery,
yeah. Well, he
right?
called it a nursery, but basically the analog of us going from random code to code that's only using functions. So the function scope and the concurrency scope.
Yeah. So if you would try to implement racing multiple computations, like a list of functions, let's say, you would simply create a scope. You would fork n threads and just wait for n of them to complete, right? And you could.
And I think there was, in our Rust implementation, there wasn't the ability to do this arbitrarily and get the single result out and cancel all the losers. And maybe that's
the cancellation issue.
Maybe that's why we needed the channel, was for that kind of the propagating that information back out.
I think
cancellation is a very interesting topic, which is actually a bit of a pain point. But yeah, let's finish on channels first. Maybe I can get back to that.
Derailing you.
So channels, they can definitely be used for that. Another area which I'm exploring with channels is there's quite a lot of very elegant and very expressive libraries for reactive streams in Scala and in Java, like Akka streams, FS2, Zio streams, and you can do really nice things with them. Like if you write the code, it reads very nicely. I think it's easy to understand, easy to maintain, and so on. So all the properties that you are interested in.
The channel becomes
the question is like, but they rely on the functional effect systems like IO, like Katz effect of IO, or on futures, right? So now the question is, what would be the equivalent of such a reactive streaming library in the world of Loom, right? Since we have a blocking. So since we can now block freely. So channels are kind of an exploration in that area as well. So the channels in Ox, apart from having like simple send and receive operations, and you can also do selects. You can select from multiple channels like in Go, but you also get those high level operations, like you get a map, you get a concurrent map where you can process several elements in parallel. You get like filter, group by. So all these streaming
starts
operators.
To look similar to the streaming API.
Exactly.
Yes. Get in
and
some of the functional effects.
Okay, you're saying that these are part of channels, that you have these operations, and
the channel would be like this stream. Like you can transform the channel.
Okay.
For example, a map is a very nice simple example. If you want to map a function over a channel, the function can be potentially blocking, right? So what you do is you start a virtual thread which receives from the channel, applies the function to each element, and sends the results to a new channel which is returned to the user. and that way you can create a pipeline of transforming elements. Each transformation would start usually a virtual thread, so that's of course imposes some cost. But again, it's like an exploration. It's not like anything that's done. More like a proof of concept.
Yeah.
So did you also say that the channel incorporates the reactive throttling into it?
Like back pressure?
Yeah.
Yes.
Yeah.
Well, the back pressure is natural because depends. So the channels can be buffered or unbuffered, right? The idea in back pressuring things is to put a bound of the amount of memory that your pipeline can use, right? So here the bound is naturally the sum of all the buffers of the channels, right? If you want to send to a channel that's full, you will simply block. So the virtual thread will block. If it will block, it won't receive further elements from the upstream. So if the downstream isn't consuming things, the buffers will fill up and everything will block, in the sense of blocking virtual threads, which is allowed, right? Because we are under Loom. Yeah. So yes, there is back pressure.
So it almost sounds like you're sort of being drawn to saying, okay, rather than the very simple channels that Go has, let's put a whole bunch of capabilities,
all the higher level stream operations on top of the channels.
Yeah, and everything into your basic channel in Aux, and then that might, I don't know, produce just much easier code to...
Well, it has two phases. On one hand, you have these high-level operations which make creating pipelines very nice. That's a good thing, right? And another good thing is that if you want to have a custom transformation stage, that's quite easy. You have the receive operation on the channel, and you can just do anything with it, right? So creating custom transformation stages and things like Akka streams is quite complex. It's doable, but it's not like easy or anything, right?
Especially if they're stateful.
Exactly. Here you can just receive from the channel, do some transformations, and send it further, right? So that's like in a mental model, that's quite simple. But there's a downside as well. So because we don't build the description of the whole processing pipeline up front, we don't really have a lot of opportunities for optimization, right? So it might be slower. Like I didn't really do any tests because I'm still at a much earlier stage. But for example, like each transformation stage gets its own virtual thread, right? That might not always make sense. It might make sense to fuse some of those. So it might be slower than... It might not be optimal.
So if you have a channel and you're doing a map and then you're doing another map, there's some overhead to those two consecutive maps.
That would correspond to two async barriers in Akka streams.
Yeah.
Right, but anytime you introduce a mechanism, it might slow it down, but the benefit of that mechanism could be, huge in many other ways, and it would be worth the cost.
It could be. Like map is also not the perfect example because there's also a variant of map which actually doesn't create an async barrier, but many other operators don't have these variants. But I guess it is quite an interesting research path. We are now working on actually improving the performance of channels to like the raw channels. We didn't get to the operators yet, and that took a couple of months of research.
You said we.
So
it's you and other people, not just
it's
you.
Mostly
on
me.
Your nights and weekends.
Well, I'm saying we because we have like a small open source research department at our company. There's like 2 people full time, and there's also other people working on various of our open source projects when they are not on a project currently, because I'm working at a consulting company. So we have like a team that's supporting our open source initiatives like Ox, like Tapir, and others.
Nice. So Ox has just to summarize, it's based on Loom. It has structured concurrency that is built on top of the JP whatever in Java, the Java JP for structured concurrency.
Yeah, the Java JEP, I guess GEP, right?
Yeah.
Java has a JEP for structured concurrency, but I think it's we are using it behind the scenes because it's quite low level. Like it's very easy to write incorrect code, which will just throw a structure violation exception at runtime. Yeah. So that's something that we fix in Ox.
And so you get the nice high-level API to just say race these things, and you don't have to think about.
It's not as flexible as the Java version, of course, but it's much safer to use, right? Yeah. So you don't. I think there's like 3 or 4 invocations that you have to do in the correct order in the Java version to get things like par working correctly, and it takes multiple lines. Yeah. In Ox, even if you don't use the high-level method, it's still much simpler and it's much harder to make a mistake.
Yeah. And then you also use scoped values, another JEP. And I'm curious, I don't know much about scoped values. Maybe you could give us a quick summary of what that is and how Ox uses scoped values.
Okay, so we don't really use them much. It's just that we provide a wrapper for the Java version so that it's usable in the Scala code. One of the pain points, I think, of functional effect systems like Katz effect and like Zio is their support for like fiber locals, right? Mm-hmm. So a canonical example is you have a correlation ID that you receive from an incoming web request, and you want to thread it through all the way down to your downstream web service call or whatever, right? Yeah. And you don't want to add an additional parameter like call ID or correlation ID to every method. It would be just painful. Yeah. So you want to put it in like a request local that's automatically attached to the whole call tree coming out from this request, right? And that's actually very hard to do in Katz effect. It's possible, but once then you go to a database and you change the monad, and then it's broken basically. With Zio, it's better, but it's hard as well. So that's why I looked at these local values, which I think is very important to have them so that people actually can use them. But our wrapper in Ox is very thin on top of what Java provides.
Okay. And really, this is just about a fiber local or an alternative.
Yeah, that's about it. So
in the virtual thread world.
Yeah, and it's like a thread local, but working better with virtual threads. It's not as mutable, you might say, right?
Yeah. Nice.
So there's only a certain scope in which you set a value, which also works nicely with the concept of structured concurrency. That the structure of the code determines like how your threads behave.
Yeah. So, one of my current understandings of structured concurrency is that it needs to be able to support reporting errors without ever losing any of them, and cancellation. So, and you're supporting those in Ox, I assume?
Yeah, so a very good question. So again, coming back to the original problem, right? Once we have an async runtime in the JVM, should we still use functional effect systems? And there's a couple of reasons why you might want to still use them. And one of them is error handling and cancellation. So cancellation is so in Java you have to rely on interrupted exception, right? On interruptions. We know they are not perfect. People have researched why they don't work in many ways, right? It's very easy to actually eat an interrupted exception, just catch an exception and log it, and then your thread will continue happily happily, even though it should finish working because the supervisor decided so, or whatever. So it requires quite a lot of discipline to actually implement interruption correctly in Java, and the same carries over to Ox. The same carries over to Scala code using Loom, right? If you want to have interruptions, you just need to keep this discipline of behaving correctly when you get an interrupted exception. And that's, by the way, the way racing works, for example, right? If you race two computations, you want to interrupt the losing one, and you interrupt it by calling thread interrupt, and
interesting, yeah.
The exception is injected over there, and it needs to be properly terminated, right?
So just as a quick example of this, in the Easy Racer, it's doing a race, and the races are against HTTP requests. And so you're using STTP for HTTP, the HTTP client in this case. And so is what you're saying is that STTP library had to correctly implement checking for interruption in STTP?
Well, no, okay, no, not going that far. Like it can't obstruct, so it just needs to make sure that there's no catch exception and logs the exception, which would simply not propagate the interrupted exception, right?
Okay.
So if we are using an STTP or another library, you are doing a blocking call. If it's interrupted, it will throw an interrupted exception. So the libraries should mostly just propagate the exception up to the caller.
Okay.
And if they do it, that's fine, right? But you still need to know if they don't do something, like maybe they catch all exceptions and convert them to something and so on, which would break things, right?
Yeah.
So that's a downside, right? In the functional effect systems, that's implemented much more nicely. The interruptions or the cancellation is like an how do you say it? Not out of bounds, but that's like a special channel
implemented in the runtime, essentially.
Yeah, yes, exactly. It doesn't rely on injecting exceptions, so you could say it's done in the proper way over there, right?
A safer, more reliable way. Yeah.
Yes, which is very hard to implement in Java right now, given all the history of Java and so on.
Yeah. Baggage, right? I think we can call it.
Exactly. Yeah. So that's something. If you decide to go the direct style route, you just need to be aware of it and maintain discipline. If you catch an exception, just in Scala, this amounts to catching a non-fatal exceptions, which would make interrupted exception not being caught. In Java, it's a bit more tricky because they are not as flexible, but possible as well. So cancellation was one thing, and the other was error handling. Yeah. Yes. I guess that's still an open question. I'm not sure how to best do error handling. I'm not sure anybody knows how to do error handling, really. There's a lot of ideas, right? We have checked exceptions in Java, but I think most people agree that they are a failed experiment.
Yep.
Right? Now the question is, why are they a failed experiment?
Yes. Why?
So,
do you know the answer?
No, I don't.
Because they don't compose.
Well, they don't compose. We were actually just discussing this last night in our book development group, and we came up with, mostly James came up with the idea that, there's a contract. Like whenever you're trying to compose things, to compose them effectively, you need to have a complete contract. It's like putting Legos together, and the contract is, one has the little pegs and one has the little holes. And if you don't meet that contract, you can't compose them. And with exceptions, there's some things that are implicit that are not.
Not unchecked exceptions.
Yeah, well, right. And checked exceptions were an attempt to
establish a contract,
to create that contract, but they weren't. I don't know. I guess maybe there's a way to escape them or whatever, and so that basically broke the whole system. If you can opt out of it, then that's not really a contract.
If you try to Google it, there's a very interesting answer or collection of answers on Stack Overflow to exactly this question. And one of the answers, I think, is going in the direction that you mentioned, that we have unchecked exceptions, which are the real exceptions. And I guess they are quite popular in all languages, right? Panics, whatever. Something goes very wrong, there's a bug, you throw an exception. And
there's no way to recover.
Yeah, exactly. And then there's checked exceptions. So there's one answer that suggests that they aren't really exceptions. It's just syntax for eithers, essentially, right? In Scala, you can write that you return either some kind of error or something, right? In Java, you have this special syntax with throws, but essentially it's the same thing, right? You need to handle the exact form of whatever the errors are returned by the method in the caller, right? So the caller is fully aware of the errors that the callee.
Well, plus you can always break the contract by throwing a null pointer. I mean, seriously, if you think of it in terms of contracts, it's like, there's always a way to get out of the contract. And it's like,
right, but that would be the unchecked exception, right? That would be the bug in the code.
Right.
So
that's really interesting.
So there's other answers over there, right? That they are not polymorphic, right? The whole, if you try to run in Java, submit something to a thread pool or run a thread, sometimes you get a runnable, sometimes you get a callable, which one doesn't allow you to throw exceptions and the other throws exception. Then lambdas can't throw exceptions, right? So it's a mess, right? So they are not. So the lack of polymorphism might be a strong indicator of why checked exceptions actually failed in Java. But there's also a lot of other possibilities, right? So in Scala, we have a couple of answers. We have unchecked exceptions. Some people like using eithers, which are very specific. Some people like using try, right? There's also the attempt to do something similar, I guess, as in Rust, to introduce a result type.
Which is really a monad.
Far from... Yes. But with syntax to unwrap it. So there's a couple of attempts to, I guess, do it. There's also an attempt to do checked exceptions in Scala, but I think it's abandoned now. It was using capabilities, so it's a bit better than the same, because you don't have to write like specialized higher order functions for each variant, which would support methods which throw exceptions and not.
Are you referring to the Caprese project, or is this something different?
That's I think something a bit before Caprese. It was the work leading to the project, I guess. But as far as I know, I think the checked exceptions in Scala are abandoned in favor of some other work, probably.
So in
developing that.
So in Ox, you need some way to know that a task failed. So, for example, a race, you are racing two things. One thing is going to produce an error. You want that to be the loser. And so the way that like Zio does it is it has the error channel that you would put that in. But in Ox, you just went with unchecked exceptions as the
so far
mechanism.
Yes. I'm not 100% convinced yet it's the right way to go. Actually, we have two approaches, kind of mixed. When we have the concurrence operators, we rely on exceptions, but we also have a retry API for resilience, because that's also in the scope of the library. And there we have variants for eithers, for tries, and for exceptions. So we actually allow users to choose. So I'm not sure if it's the best way to go, and I would love to settle on one approach to error handling, but we simply didn't come up with it yet. So that's something that we want to develop in the future.
We discovered something interesting last night that I didn't know about Zio, but it's that if on a Zio you can call a retry, a number of different APIs for that, but it actually uses implicit evidence to verify that you actually have your Zio has an error in the error channel, or the compiler won't let you call retry. And I thought that was a cool way, as we were talking about like contracts and the how how when you have a contract, it allows you to know things when you're composing stuff together, and that was a cool example of Zio's ability to have a contract around the air channel and have compilers if you
and enforce that contract at other places.
That, yeah.
I do really like that what you pointed out about exceptions, because you often see people saying, okay, so there's two kinds of exceptions. There's recoverable and unrecoverable. And that has always it's always bothered me a little bit. But then when what you read pointed out that, well, these are really two different things.
Mm-hmm.
A quote unquote real exception is the unrecoverable kind. And then the other thing is what it's an error that you're supposed to handle.
Mm-hmm.
And what
I really like Rust's way of just saying, like, anything potentially recoverable is a result, and anything unrecoverable is a panic.
Mm-hmm. Mm-hmm.
I guess that's not far away from the Zio approach as well, right?
Oh, yeah.
And I guess Zio is really nice when it comes to error handling, and it gets a lot of things right. So again, the question is like, when you want, if you are using Zio, right, you get cancellation, which is principled. You get error handling, which is very well done, but you get the syntax, you get the stack traces, and you also get the virality. So, you have to balance it out.
Yeah.
In the end.
Yeah.
It's interesting. Well, in Python structured concurrency, it allows cancellation because at the determined suspension points, it knows enough, and it actually performs. Those are safe points to perform cancellation, and so you can. The cancellation is built in, and the error reporting is also built in because it knows those safe suspension points. And I don't know if that could be something that would help.
Well, yeah, these safe suspension points would be like whenever you block, right? Which could be anywhere really, because you don't know. So I don't think we'll be able to detect that. So I think we will have to live with cancellation as it comes in Java. Meaning interrupted exception, but I think we might be able to come up with something nicer for error handling. Not sure if it's going to be unchecked exceptions. I'm hoping it's going to be something better, at least for people who really care about what kind of errors. I think maybe something result like, well, I don't know. It's like probably another topic for longer research, but it's definitely something that we need to work on, and we need to research and develop. So that's an open question still.
So if you have a few minutes, I want to talk a little bit about your benchmark that you did recently with Loom and coroutines. Can you give us just the rundown on what your benchmark was doing and what you discovered?
Sure. So the original cause for doing these benchmarks is that I wrote like a maybe not very simple, but a straightforward implementation of channels in OGS with support of selects, where you can select exactly one value to receive from exactly one channel. And then I ran some Kafka code with it and so on, just to see how it feels to program with it. And it worked, but it was really slow. So, it was a proof of concept, and the concept was proved, but it was slow. So then I got interested into looking at how this can this be made faster.
Why was it slow? Yeah, and how can you make it faster?
Yes. So I arrived at Kotlin channels, which they have the same concept, and they also arrived at the same conclusion that channels might be a good idea to communicate between coroutines in their case, and that run concurrently, and they also support selects and so on. So there's like a paper into how they implemented this in Kotlin, and it's transferable to Java as well. But before doing the whole implementation, I just wanted to see if using virtual threads, the approach makes sense at all, right? So I started with a benchmark where I had a number. I wanted to pass, I guess, 10 million values from one thread to another through some medium, right? And in one case, it might be an aux channel. In other case, I also looked at Kotlin, how fast using their channels this happened. I was looking at synchronous queue in Java, at array blocking queue, and some hand-rolled implementations, right? So that was the idea of the benchmark.
Like how quickly can you pass 10 million values from one thread to another, and given different implementations?
And it was done in a rendezvous way, meaning that the two threads have to meet to exchange the values, right? So there's no buffer or anything. You send on one thread, and the other thread must call receive, and the send won't unblock until the receive is there, right? Okay. So they have to meet and exchange the value. So that was like the limitation. And it turns out like Kotlin is really fast, and the coroutines implementation there is really performant. And it turned out to be the fastest among the contenders.
And I do remember the research paper that was based on. I haven't read it, but I'll see if I can find it and put it in the show notes, because it's an interesting one. You've got it printed out. That's awesome.
Yeah, I prefer reading printed stuff. Fast and scalable channels in Kotlin coroutines.
Awesome.
Yeah, very nice paper, by the way, and a very nice implementation. Yeah. So but there's a catch. So I did the micro benchmark, and it turned out that Kotlin is the fastest. And then if you do some performance optimizations in the Java version, like synchronous queue was really slow. There's a thing called exchanger in Java, which was much faster. A bit different use case, but worked for the benchmark. And then if you did some code, some custom code, which implemented this exact scenario, you can also get very good performance, very close to the Kotlin one. So this looked promising, right? The virtual threads can actually do it. But then, and I implemented this I implemented this paper in the Java. So that's called JOX, like Java Aux, but it's only the channels implementation.
Sure.
And in these micro benchmarks, like it's very fast and everything. But the catch is that then I posted it on Reddit, and Ron Pressler came. He's one of the members of the Loom team who actually implemented this. And he says that, micro benchmarks should be ignored unless you're a JVM tuning expert, which I'm not. And that actually, the Java version is faster than the Kotlin one. Because still, like if you implement the paper and you do the micro benchmark, you get really good results under Java and virtual threads, but still Kotlin is a bit faster, right? So I implemented some benchmarks which weren't micro benchmarks, but were running things at scale. So in the latest benchmark I've done, I have 10K threads, and now you have to pass a value from the first thread to the last one, right? So they do it like in sequence. So there's a lot of concurrent work going on. And if you run this...
you're saying you pass the value through all 10,000 threads?
Yeah. So that's, in the middle of the benchmark, there's like a lot of things happening, right? Because they all work at the same time. And this indeed proved Ron to be correct. Maybe not entirely, but mostly. In
that virtual threads were really efficient at
the Kotlin is still faster, though. Kotlin is still faster, but now my implementation of channels is about the same performance as Java's synchronous queue. So the difference, there was a huge difference in the micro benchmark comparing the synchronous queue to like custom code. But if you run at scale, this difference disappears. Kotlin is still a bit faster, but they are both really, really fast. So both the channels, the Java concurrent data structures, and Kotlin.
So in aux, will you rebuild the channel implementation on top of JOX?
Yeah, that's the plan. So you might wonder, like, what's the benefit of actually having channels, since they are comparable in performance to a synchronous queue? But there's some very good reasons. First of all, a channel is completable, meaning you can actually say normal elements will be sent to this channel, or then this channel is in an error. So there was an error processing, right? So you close the channel. Not something you can do with the queue. So that's one thing. And the second thing is that it supports selects. So you can select exactly one value from a number of channels to receive or to send.
Okay. Yeah.
So this enables the Go style programming at performance levels, which are, I can now say, the same as Java's or Kotlin's more or less.
So would it ever make sense once you kind of flesh Ox out to make a Kotlin version of it? I guess you could call it Cox, but I don't know how that would go over. But
no, the Kotlin version is out there.
Oh,
so,
really?
Yeah. It's all. So the paper that I'm basing on is describing an improved implementation of channels in Kotlin, and they are using coroutines, of course. I'm using virtual threads. So the code is a bit different at the very low level, where we actually have to suspend. Right, so they use coroutines. It's all coroutine based. I'm just using at a very low level lock supported Spark, which blocks the thread.
But those are channels. Is it not the whole Ox architecture?
Yeah. Those are channels. Well, they have their own approach to structured concurrency. So
that's good enough.
It's a bit different, of course, in terms of the API. But yeah, it works there and it works really nicely. So yeah, Kotlin is definitely a very good source of inspiration here.
Nice. Cool. Well, that was super educational. Do you have anything else you want to add or cover?
Well, I would love to join your conference one day. It really sounds great.
Oh, we'd love to have you.
Not this year, unfortunately, but maybe next one.
Okay. All right. We'll get you here next year.
That would be.
Yeah, I'm following it for a number of years, and I always wanted to come there.
It's a long trip.
It is a long trip.
It is a long trip, but I've done it a couple of times. It's survivable.
Oh yeah, no, it's a good place to go.
But you've been in Europe as well. It's the same trip.
Oh yeah. Of course.
In reverse.
The whole trip and the jet lag and everything. But this is I find that's mitigated a lot if you're going to a really comfortable place, and we like to think of Crested Butte as a very comfortable place to show up, and the conference itself is very, very welcoming and friendly and engaging. So
awesome. Well, Adam, thank you so much for spending your Friday evening with us. I really appreciate all of your amazing open source work that you do. And
thank you.
And
thank you for the podcast. It's really great.
Thank you.
I love listening to it. So it's really good that you guys are doing it.
Yeah, this has been a super useful conversation for me.
Yep. Awesome.
Bringing a lot of things together. So thank you very much.
Thanks, Adam.
Okay.
Bye.
Thank you.